Thanks very much for that kind introduction. But since this is a pre-recorded talk, I have no idea what was said. But whatever it was, I'm sure it was greatly exaggerated, particularly maybe the unflattering parts. I'm very much honored to speak at this meeting. Psychonomics has always been very close to my heart. I eagerly look at the program every year, such as this mock-up of the program here. Now, I'm what you would call a language person. I go to all the language sessions, but I've always had a love for learning and memory as well. And as you know, at the meeting, the language and memory sessions are always opposed to one another. So you can't go to both of them at the same time. So when I first started out at Psychonomics, I used to always go to the language sessions and avoid all the memory sessions. Then later on, I kind of learned to pick and choose and go to some, not the other. Of course, eventually, as I got older, went to fewer and fewer talks and kind of hung out with people I know instead. So that's a less ballroom and more barroom, I suppose, would be the way you could characterize it. So how does this talk fit in with this? Well, today's talk deals with my theory of learning in language production. So it's going to deal with both language and memory. So we're going to have to go back and forth. And actually, the theory is composed of 4 what I call mini-theories. We're going to start with a production mini-theory in the language domain. Then we're going to move over to the memory side and present a theory of implicit learning. Stay on the memory side for a theory of consolidation, and finally move back to a developmental psychology, a developmental account of language. So let's get to the official formal start of the talk. And let me start by first acknowledging all my main collaborators, and they're here pictured for you, and then lots and lots of other people who have helped in many, many ways. I'm going to start with some kind of hardcore linguistics. I'm going to play for you 2 language samples. The first is Russian, and the second is Persian. So here we go. This is Russian.
Произведения Баха звучат совершенно по-другому, чем произведения Шонберга, так же, как звуки персидского языка отличаются от тех русского языка.
And here's Persian.
قطعات باخ با موسیقی شونبرگ از نظر سبک تفاوت اساسی دارد. درست همانطور که صوت زبان فارسی با زبان روسی متفاوت است.
I hope you could tell these sound really different from one another, and they also sound really different from English. Part of these differences are what's called phonotactics. The word phonotactics is like the word syntactic in the sense that syntactic rules are rules of how words combine to make sentences. Phonotactic rules are rules about how phonemes combine to make syllables. Let's look at some of the phonotactic rules of English. Just consider this syllable, hing. That's not a word, but it could be an English word. It sounds sort of English-like. But if you reverse the order of the consonants to this, it sounds like this. It's hard for me to say it, but I'm going to try. That doesn't sound like English. In other words, it's phonotactically illegal. And that shows that there are particular rules about how to build syllables. What we call first-order rules are general rules about where particular consonants occur. The H consonant has to be at the beginning of a syllable. It can't be anywhere else. And the NG consonant has to be at the coda position or the end of the syllable. There are more complicated rules too. They might depend on context, and we're going to call these second-order rules. And this is a little complicated, but I'll go through it. If there's a prevocalic R, then D can be an onset, but S can't. In other words, we can say drip, but we can't say srip. But if there's a prevocalic L, it's the reverse. S can be an onset, but D can't. So we can say slip, but we can't say slip. Okay. I'm claiming that these rules, English speakers implicitly know them. So how do we know that they implicitly know them? So let's talk about how we can detect implicit knowledge. Well, Sigmund Freud had the idea that we can detect implicit knowledge by looking at speech errors. Here is our president. One of his more famous speech errors back when he was a senator from my home state of Delaware. He said, "Many of us were in Rome at the president's funeral." Excuse me, Freudian slip, at the Pope's funeral that the president attended. Pretty unfortunate slip. And of course, Freudians would say, very interesting, and interpret this as some unconscious wish for the president, who was George Bush at the time, to have a funeral. That's outlandish. But Freud was right. Slips do reveal unconscious knowledge. They just reveal unconscious linguistic knowledge. And here I'm highlighting the linguist Victoria Fromkin, who emphasized this. So slips reveal implicit phonotactic knowledge. How do we know this? Because of something called the phonotactic regularity effect. Slips rarely create illegal sequences. So let me give you an example. So suppose I'm trying to say the word none. If I said nung instead of none, that would be phonotactically legal because the ng is in the right position. But if I said none instead of none, that wouldn't happen. That's illegal. So the slips sort of reveal that we know this. Let me play for you again one of the speech samples that I showed you before. I'll show you the Persian one. It's spoken by Bani Nazari, and show you what the translation of it is.
قطعات باخ با موسیقی شوئنبرگ از نظر سبک تفاوت اساسی دارد. درست همانطور که صوت زبان فارسی با زبان روسی متفاوت است.
So what Bani is really reminding us is that different languages really sound different. They have different patterning of the sounds in the same way that different music has different sounds. So she's emphasizing the differences between languages. Linguists tend to focus more on the similarities among different languages, and they do that because they want to discover the basic universals. But Bani, as a psychologist, is interested in the differences. Psychologists focus on the differences, and we attribute these differences to learning. That's what this talk is about. We're going to focus on phonotactic knowledge, and we're going to use speech errors to investigate the nature of this learning. Okay, here's the basic experimental paradigm. The question is, can new phonotactic constraints be learned and influence speech errors? It's a really simple experiment. People just say strings of 4 syllables like this. Hes, fang, neg, kem. Hes, fang, neg, kem. Hes, fang, neg, kem. That's it. That's the way a trial goes. But every single one of these sequences will have different kinds of consonants. So there will always be an H and an NG, and these will be distributed as they are in English. H has to be an onset, and NG has to be a coda. We call these language-wide constraints. The crucial part of the experiment is we pick 2 other consonants and make them behave like H and NG throughout the experiment. So F has to be an onset throughout this whole experiment, and maybe S has to be a coda. And then we can compare them to the other consonants, which we call unrestricted. And here we see that K is an onset, but maybe in the next trial it could be a coda. So they're not restricted in the way that the other consonants are. And what we do is we just look at the speech errors that people make when they have to say these things. So first of all, we could look at the speech errors in which H or NG move. So instead of saying hes fang, you would say hes hang. And so the H is moved from an onset position to another onset position. What we say is it's maintained its syllable position and to obey the rule in English that H has to be an onset. So that's evidence for knowledge of the rule that H has to be an onset. For the experimentally restricted sounds, we can do the same thing. So suppose that instead of saying hes fang, you say fes fang. We could also ask whether the F tends to move to onset position. And what we'll be keeping track of is whether F as an onset moves to another onset position to obey the new rule. And then finally, we need to compare that to other slips where the sounds are not restricted. So here we have a slip where K is an onset in this sequence, and we can look to see whether K would then also move to an onset position. In this example here, instead of saying neg chem, speaker says nec chem, so that's an onset to coda slip. And we would say that has changed the syllable position. So what we're looking at is whether the slips change or maintain their syllable position. So that's what is on the y-axis here, syllable position maintenance. And this experiment was a long experiment. People did this for 4 days. And what you're going to see are how often the slips maintain their syllable position. First of all, for slips of H and NG, every single one of them, there were hundreds and hundreds of slips like that in this experiment, every single one of them maintained its syllable position. That is a manifestation of the phonotactic regularity effect. Because the speakers are English speakers, they know this very well, and their slips follow the rules. For the slips of unrestricted consonants like K, G, M, and N, the slips maintain their position a whole lot less, 68% of the time. That's a big difference. But it's bigger than 50%, so there is some tendency, if F is an onset, it will tend to move to another onset position, but it's not a strong tendency. That's something that's known as the syllable position effect. Finally, let's look at the experimentally restricted items. This is the crucial data. 98% of the time, slips of F and S maintain their syllable position when they slipped. And so that's much bigger than for the unrestricted sounds, and that is the evidence of learning. And we're going to call this difference here excess legality. We claim that the excess legality of these restricted consonant slips is a result of implicit learning, and implicit learning inside the language production system. So why is it implicit? Well, we try to do experiments where we tell people the rules. We say, hey, when you're doing this experiment, every time that you say an F, it's going to be at the beginning of a syllable. Make sure you remember that. Telling them this has absolutely no impact. Or if you don't inform speakers about the rules, you can ask them, well, did you notice anything about some of the sounds? They're completely oblivious. They have no idea. And the final point I want to make, and this just goes back to Sigmund Freud, the data that we're looking at are slips. They're things that you didn't intend to do. So because this is not intended behavior, it sort of naturally reflects what you implicitly know. Now, why do we say that it's internal to the production system? Well, a number of experiments have been done that show that if you hear syllables that follow rules, you'll learn that, but that will not influence your slips. So the learning that we're talking about is internal to the production system. Okay, here's our theory. And we're going to break it down by presenting 4 mini-theories. The production theory, the learning theory, the consolidation theory, and the developmental theory. And we'll start with the production theory. And the goal of the production theory is just to explain where phonological speech errors come from. So, it's very simple. Phonological slips happen during something that's known as syllabification. So what's syllabification? When you intend to produce a word or syllable like cat, you activate that word, the activation spreads to its phonemes, k, a, t, and then you put them into slots in a syllable frame. That's the process of syllabification, building syllables from retrieved lexical information. Now, no one really is going to make a slip just saying the word cat. Slips happen when you have to say a bunch of syllables close in time to each other. And so we need to have a theory of how we produce serial order with syllables. The crucial features of this theory are primacy gradient and inhibition of the past. Now, the primacy gradient is here illustrated on the slide that you can see. If you're trying to say something like cat came home, cat is the most active, and then came, and then home. So you're ready to say the thing that's most activated. After you've said cat, though, it gets inhibited. That's inhibition of the past. And now came is the most activated. And so this produces serial order. In fact, it produces what we call a moving attentional spotlight on the current syllable. And slips occur when phonemes from nearby syllables are mistakenly selected. Bonnie Nazari and I refer to this as feature migration in time. For those of you who know about theories of visual search, this is exactly the same phenomenon, except not in visual and not in spatial things. It's motor and temporal. And so you can see slips like this. Instead of saying came home, you would have hame home, or instead of came home, you would have came comb. That's it for the production theory. Very simple. Now let's turn to the real meat of the theory, the learning theory. How do you learn to produce these phonological sequences? Central idea is very simple. Each time you say something, each act of production is an act of learning. So when you put a particular phoneme in a particular position in a syllable, that just increases your ability to do that in the future. This simple idea explains the three things we've talked about so far: the phonotactic regularity effect, the syllable position effect, and the excess legality of newly learned rules. So let's start with the idea that when we speak, we have cues, lexical and phonemic cues, things that are helping us to build the syllables, and we have to learn where to put these in the syllable frame. The phonotactic regularity effect arises simply because we have a lifetime of experience of every time we said an H, we put it in the onset slot, and every time we said an NG, and this funny looking symbol here is the phonetic symbol for NG, it goes into the coda slot. The syllable position effect happens when we learn to put particular phonemes in particular slots in the context of particular words and syllables. So when we're trying to say the word sing, S goes in an onset slot, and that causes the syllable position effect. And then finally, the excess legality of newly learned rules. If you're in one of our experiments and F is an onset, or actually I think the example I have is S is a coda, you gradually build up over time an association between that, and that explains this. We can make this idea more concrete by actually building a simple connectionist model. And here's the model we call the adaptive syllabification model. It learns to map from the lexical and phonological cues to assign them to positions in the syllables. And it learns it by simple connectionist learning rules such as backpropagation. So you start out and you train this model with English syllables. And after it's been trained, it exhibits the syllable position effect and the phonotactic regularity effect. So let's have it try to say sing. When you give it sing to say, it will activate S as an onset, I as a vowel, and NG as a coda. And crucially, S as a coda is pretty much unactivated because the model has learned that the S belongs in onset position when sing is activated. It also shows the phonotactic regularity effect because the NG can never occur as an onset, and so it's almost never, ever, ever active. It's very, very close to zero. It's as if this unit has sort of disappeared from the network. There's no way you can get there. If we take this model and train it in one of our experiments, give it the syllables that are in the experiment, and look at the activations that it produces, what you see is it learns the rule. F is an onset and S is a coda. The the excess legality in the model increases as you train it more and more. And that's shown here in this slide. So that's learning. So what is this learning like? So there are a number of features. It's incremental, subject interference, error-based, able to learn complex rules, constrained by input. In short, it's like a lot of connectionist sequence learning models. So let's look at some of the evidence. Suppose you take this model and you train it that f is an onset. Gradually over time, what you see is that excess legality goes up and up and up and up for s as an onset. But then if you just flip it and now start training the model that f is a coda, it'll go back down again. In other words, the model incrementally learns, and once it gets somewhere, it starts unlearning. And it's hard to sort of learn the new rule because of proactive interference. We can run an experiment like this too, and what we see is pretty much the same thing. You see when you learn that f is an onset, you see the subjects in the experiments, their slips show good excess legality, but then when you reverse it, the subjects have a lot of trouble learning the reversed rule because of the proactive interference from the original training. Next, let's look at at evidence for the error-based learning. So what do I mean by error-based learning? I mean that the learning or the weight change in the network is proportional to the target or intended activation minus the actual activation. So if the system is doing what it's supposed to do, it doesn't learn. It only learns when there's some degree of error. How can we test this? Well, we can do this by an experiment in which we have subjects, say, one of these sequences, say, in which f is an onset at a reasonably fast rate, so you get a lot of errors. And then on the next trial, you say it at a very slow rate, like Hess, Fess, Bang, Bang, and we reverse it, so now f is a coda. Third trial, we go back to f is an onset at a fast rate. Fourth trial, f is a coda at a slow rate, and so on, up to 96 trials. So the idea is if we have the slow trials be the reverse of the fast trials, and we know that slow trials create much, much less error. There are very few errors at the slow rate. If the learning is error-based, the slow reverse trials will not impact the learning from the fast trials. And that's exactly what you see in the data. If you run this experiment in which the slow trials have exactly the same rule as the fast trials, you get around 0.19 excess legality. And compare that to where the rules are the reverse, it's only slightly less. And so this is evidence that the reversed mapping on the slow trials isn't really impacting anything. Why? Because there's less error. The model is also able to learn complex second-order rules. Well, we can look at these second-order rules by a situation such as this. We could make where the F and S are supposed to appear contingent on the vowel. So we would have a string in which the vowel is a, has, I can't say this, has, fang, nag, cam. And then the next trial will have a different vowel, sif, hic, mig, ning, and so on. And so we would alternate A, I. This is called interleaved training. And the constraint in the experiment would be F is an onset and S is a coda if the vowel is a, but F is a coda, S is an onset if the vowel is it. In other words, the reverse. That's an example of a context-dependent or second-order rule. If we train our model to do this, it learns it. It doesn't learn it quite as well, but it learns it. The reason it doesn't learn it quite as well is because there's a lot more interference in learning this kind of rule. And the reason the model is able to learn it, crucially, it has hidden units. That is, it has representations that are capable of keeping track of something like F in the context of A. What happens when you actually do experiments like this? Well, there are many examples of experiments that have been done that show successful second-order learning in these experiments. There are a great many experiments showing that slips will obey a second-order vowel contingent constraint. Also, consonant contingent constraints, I'm just going to skip over that. But a particularly interesting one is this last one, the stress contingent constraint. So here the rule is a little bit complicated and a little bit strange. F is an onset, S is a coda if the syllable is stressed, but the reverse if the syllable is unstressed. It turns out that people's slips will obey this rule. So there's a real ability to learn these second-order rules. Here's a rule that English speakers can't learn. It's a rule based on tone. Now, English is not a tone language the way Mandarin Chinese is, but English speakers use tone all the time. What we did is we asked people to say strings of these syllables with different tones. So sometimes they had to use a rising tone in the sequence, like hes, fes, may, wait, I can't even read it. Hes, feng, neg, kem, hes, feng, neg, kem. That's a rising tone. Or a falling tone. Hes, feng, neg, kem. These correspond, by the way, to two of the tones of Mandarin. And we embed a rule, F is an onset and S is a coda if the tone's rising, like that, or S is an onset and F is a coda if the tone is falling. Will the slips obey this rule? And the answer is no. And we also checked on another day, and they still didn't do it. So it looks like this is unlearnable. And that leads to this second point. English speakers can't learn based on tone, but they can learn a rule based on stress. And so we think that the input to the learning system has to be something that's linguistically distinctive in your language. That is something that distinguishes lexical items. Okay, let's look a little bit more closely at the data for learning these second-order rules and first-order rules. So I'm going to plot, a lot of these experiments are multiple-day experiments, so I'm going to break down the data depending on what day it occurs. So up at the top here, there are many, many experiments investigating first-order rules, like F is an onset throughout the experiment. These are all learned quickly. It shows up on day one. It's at the maximum on day one. What about second-order rules on day one? Uh-oh. There's no learning. Second-order rule based on the vowel, this has been done several times, about 10 times, or ultimately. There's no evidence of learning. So I've told you these rules are learnable, so when does that happen? It happens on day 2, day 3, and day 4. That suggests that something magical happens between day 1 and day 2, possibly that it's learned after sleep. So we need to move on to the third mini-theory, the consolidation theory, that perhaps something is happening in that period of time. So the hypothesis is that a sleep period is needed to consolidate second-order learning. Turns out it does seem to depend on sleep. It's a very nice experiment by Gaskell and colleagues. They broke down the half of their subjects were in the wake group and half the subjects were in the sleep group. And what they did is they trained on a second-order rule for a while, and then they waited in the wake group. They waited for 90 minutes, and then they were tested again. And what you see is that there was no excess legality. The sleep group did exactly the same thing in the first session and then took a nap for 90 minutes, and bang, you see the learning. That suggests that a sleep period is needed to consolidate the learning. So how does this work? Let's take a step back and sort of remind ourselves that in the first session of these, everybody can learn first-order rules, and they can't learn second-order rules, or at least they don't give any evidence of learning the second-order rules. And I've already told you that you need hidden units in a connectionist network to represent the second-order rules, to represent the fact that F in the context of A. So it's kind of as if the hidden order rules aren't there. So what happens in the second session after sleep? Are there magically hidden units there because it is sensitive to second-order rules? Well, what we think, and this is just a hypothesis, is that you use the hidden units on day one, but their connection strengths only change after the consolidation period. So let's look at some way to test this. It's a little bit convoluted, but a crucial prediction of this idea is that what is consolidated while you're asleep is the net potential learning on day one rather than the experienced items. And we can test this by eliminating the net learning by blocking the items in some way. Let me show you what this means. So let's focus on a second order rule that I've kind of written out here. F in the context of A has to go to an onset. S in the context of A has to go to a coda. And then the reverse with a different vowel. What if on day one we blocked the trials by vowel? So we did a bunch of trials where it's nothing but A. And then for the second half of the experiment, in block 2, we shifted to the trials in which the vowel is I. And then we let people go home, go to sleep, and when they come back, we'll interleave the trials, and we'll see what happens. Is there going to be consolidation? Is the rule going to emerge when things are blocked? Well, what would you predict from a model? It turns out if you block by vowel, training by vowel in a model, you don't learn the rule. This is true regardless of whether you have hidden units or not in the model. So let's look at what happens when you train on block 1. So when you train the rule for the vowel A, so this line going down shows that you're learning. That is, that the model is learning these patterns. So there it goes. It learns it just fine. Then on block 2, we shift it to the other pattern, and 2 important things happen. First of all, your ability to learn the I pattern starts way up here, so you're experiencing proactive interference, and also, as you learn the I patterns, you unlearn the A patterns. The net result of this, so this unlearning effect is sometimes been called catastrophic interference, and it's something that occurs in neural networks. And so the end result of this is that you haven't learned the second order rule at all. You're back where you started from. See, there's nothing. You sort of moved around a lot and ended right back at the beginning. So is this what happens if you actually run the experiment? Well, if it's the case that consolidation consolidates the net learning, there is no net learning. Therefore, it's predicted that you won't see the rule on day 2. So let's check at the data. So first, let's look at block 1. Of course, you're learning half of the rule, and the slips will follow that rule just fine. Now we shift to the other pattern, and because of the interference from the other pattern, we don't see any evidence that that's learned. The crucial result is what happens on day 2. We've been exposed to all the items a lot, but they've been blocked so that there's no net learning. And what you see on day 2, when you interleave the items, is no learning at all. So therefore, the prediction is confirmed. There's no learning if the net learning is consolidated. Of course, if you had used interleaved training on day one, you would see the learning, and you do see this. So it looks like we characterize the learning like this. Second order rules are learned after consolidation of an interleaved session. And so we have to plot the data in terms of days of interleaved training. And we've done a few more experiments, so I'm going to add these others to that. So that's a kind of a nice generalization. It tells us something about consolidation. Unfortunately, I haven't told you the whole story. There's one point that I haven't plotted on this graph, and so it almost pains me to do so, so I'm going to plot it right now. There it is. Up there, there is one study that showed very powerful second-order learning on the first day. This was done by Smalley and colleagues, and it's 9-year-old children. Now, maybe there's something strange about their procedures or anything. What happens if they also tested adults, and the adults are down here? So there's something about kids. These kids are exceptional learners of these artificial phonotactic rules. This brings us to the final mini-theory, the developmental mini-theory, where we have to explain these effects. Let me start with some quotes. These are some of my most favorite quotes in psycholinguistics. First of all, less is more. Alyssa Newport suggested that children's remarkable ability to learn language is paradoxically because of their poor processing and memory abilities. It helps them learn linguistic generalizations. Related to this, Seidenberg and Zevin point to the paradox of success. If you already can do something pretty well, that impedes future learning. And then finally, from Nick Ellis, the limitations of second language acquisition derive from basic learning principles. So put this all together, and here's our hypothesis about what's going on. Children are better learners because the learning is error-driven. In adults, the successful prior learning, adults' ability to do these tasks pretty well, blocks or prevents new learning. So if this is true, if the learning is error-driven, we can explain the data, but we're going to need one additional assumption, and that's the assumption of conservative weight updating. Small changes in hidden unit connections are postponed until after sleep. Okay, maybe this explains it, but do we know that the children are more errorful in this task? Do the children make more errors? Yes, they definitely do. They make almost 4 times as many errors in this task where you have to say hes, feng, neg, chem, and so on. So what's going on? We argue that strong lexical cues in adults block the learning of new second-order rules because the learning rule itself is based on error, which creates cue competition. So let's take a look at it. So suppose we're learning to say the syllable fee. So we have, and we're trying to learn that F is an onset when we're trying to say fee. Well, we have a lexical cue that whenever we're trying to say fee, F should be an onset. That actually is a very, very, very strong cue. There aren't really any other cues that are going to matter that much because F by itself doesn't really tell you whether it's an onset, or F in the context of I doesn't tell you that it's an onset. So if you actually were to train a model, and we did train a model like this, and looked at, so we trained a model for several epochs and looked at the connection weights. And what you see is that there are strong lexical cues. It's the words and syllables that you're intending that determine where you put the phonemes. And then we compared it to a child model that just had less training. And what you see when you do this and look at the model's ability to learn second order rules after you then put them through the experiment. Oh, so the child model, I forgot to mention this, the child model, the lexical cues are weaker. The children have less knowledge about the words. That's the main thing. But the child model is capable of learning the second order rule much, much better. Why? Because they don't have prior learning that enables them to do the task without learning the new rule. So they learn the new rule very effectively. Is there some way we can test this idea? Well, the way to test it is try to find situations in which there's a high degree of error with adults. And we've looked at this in several domains, but I'm only going to tell you about one. It turns out that if you run older adults, that is people as old as I am, they are as error prone as children in the task. Now, older adults don't make a whole lot of slips. That's mostly because they slow down. But if you put them in this task, it's very, very hard. They slip as much as 9-year-old children. So that predicts, if this error idea is right, that they should be able to learn the second order rules on the first day. So here's the data that I've already presented you. Let's see what happens with the older adults. Bing, right up there with the children. They've learned it on the first day just fine. And in the discussion section, we can talk about some other things we've done to test this idea. Older adults learn the second order vowel contingent rule on day 1. Okay, let's summarize. Here are the second order rules for vowels that we've talked about thus far. That shows that learning these requires a consolidation period. I told you that speakers are able to learn a second order rule based on stress. But does that also require consolidation? Yes, it does. You don't see this on the first day, but it comes out on the second day just the same. So one kind of pattern that we see in this data is a learning pattern that requires consolidation. There's a second pattern. There are rules that you can't learn, that they're unlearnable. I've already told you about the tone effect. We've also tested a speech rate contingent rule that was not learnable. So that's another pattern that you see. And then finally, we have these rules that can be learned quickly. So these 3 learning patterns, quick learning, consolidation-based learning, and unlearnable, provide really strong constraints on the theory. So what have we learned? The production mini-theory says slips occur from phonemes when phonemes from nearby syllables are incorrectly put in frame slots. The learning theory says when you produce a syllable, you increase your ability to produce that syllable and syllables that are similar to it. The consolidation mini-theory emphasizes that learning new second-order rules may require consolidation of net learning. And the developmental theory says the need for consolidation varies with age, possibly reflecting the amount of error. Okay, let's sum up. Why do we like this domain? I've been working on it for 20 years. Why do I like this particular domain? It's an unusual one in psychology, in experimental psychology. You might remember that Steve Pinker referred to speech errors, in particular speech errors such as "mommy goed home," as the Drosophila of psycholinguistics. It's something small, but something that is quite revealing. I think these slips are revealing in a similar way. But our method uses speech errors. We're not counting how often people slip. We're using the speech error patterns to measure implicit learning. No reaction time, no error rates. A particularly important thing about the result is that the consolidation effects are dramatic. There's no learning on the first day, but full learning on day 2. The only other example of this in language that I know of is the consolidation of vocabulary discovered by Gaskell and Dumais. This is known as the Cathedral effect, and people can ask me about that. This research is the first that I know of to really link research on critical periods for language learning with consolidation. And I think this is something that we should be investigating. Finally, there are just lots and lots of predictions to test. Whenever I tell people about this, they say, oh, did you do this? Did you do that? Did you do this? There's so much to do. I mean, for example, native speakers of tone language should learn new tone-based rules, unlike our English speakers. There are many, many other examples, and we can perhaps discuss them at the end, which we have now arrived at. So thanks very much. And again, I want to thank all of my collaborators on this project and many, many colleagues and other researchers who helped along the way. Finally, I also want to thank Steve Drake, Dwayne Watson, and Tiffany Aurora for technical assistance. I have no idea how to do this recording otherwise. Finally, Sigmund Freud, Victoria Fromkin, and Joe Biden for their inspiration. Again, thank you.